All right, let's take a look at another example, this time of somebody at the movies. Okay, this might be a problem relevant for somebody who owns a movie theater and they have a certain number of people who come in every day and they make some money off of differently priced tickets, and they want to know some demographical information about who's coming to their theater, right? Maybe they want to know, based on the sales, how many adults are coming, or how many children are coming, or how many seniors are coming, and based on that, they can either adjust their ticket prices or use that information to select different movies based on who's coming the most often, right? If lots of kids are coming to their theater, they're probably going to want to show more kids' movies than adult movies, and vice versa. Okay, so a movie theater charges $11 for an adult ticket and $8 for kids or seniors. Okay. That's kind of standard movie prices. I don't know if kids get discounts nowadays. Maybe it depends on the theater, but $11 for an adult, $8 for a kid or a senior. So let's suppose that on one particular day, 240 people attended the early movie. The early movie just means the first movie of that day. There's no matinee prices or anything like that. So 240 people came to the first movie, and ticket sales for that movie totaled $2,370. And notice right now, we don't know how many adults came and we don't know how many children came. All we know is that in total, there were 240 people. And based on those 240 people, we made $2,370. So the box office manager wants to know how many adults came, right? Again, he could use that information to make decisions about ticket prices for the future or about what kinds of movies to show in the theater. So, what kind of system of linear equations could we write to help the manager figure out the number of adults? Well, here's a couple tips when you're dealing with problems like this. Whenever you see a total mentioned, a total amount, okay, like we do here, we have the total number of people and the total number of sales. So we have two totals, in fact. Those problems, those total problems, can be modeled using general form. And I'll show you how to do that in a moment. Okay? So just to recap, slope-intercept form was good for problems where you have a base amount plus a rate. Total problems are good for, general form is good for modeling problems where a total is mentioned. Okay, so there's a key there to help us out. Another tip here, another struggle that students sometimes have is trying to figure out what variables to use. What letters should I use and what should they represent and things like that. Often a problem will give you a hint as to what the variables should be by asking you a question like how many or how long or how much. Questions like that usually indicate one of the variables that you should be using in your equations. And you'll notice right here we have the term how many adults, right? So the number of adults is going to be one of our variables. So we're going to use the letter A to represent the number of adults. What would our other variable be? Well, like I mentioned before, we don't know how many adults there are, and we also don't know how many kids there are, or seniors. So we'll use C to represent the number of children / seniors. And now for the model. All right, so what we're going to do is we're going to create two linear equations, one that represents revenue, the total revenue brought in by the movie, and the other one represents attendance. Now, how do I know that my equations are supposed to be about revenue and attendance? Well, the hint is in what the totals are about, right? I have one total that tells me the number of people that came, and I have another total that tells me the amount of money brought in, right? So each total gets its own equation. That's how I know that one should be about revenue, total money brought in, and the other should be about attendance, total people who came. Okay? So let's think about revenue, right? My total revenue was $2,370. How was that amount created? Well, ticket sales, obviously. How would have that happened? Well, it's $11 per adult. So to figure out the amount of money brought in just by adults, we would go 11 times how many adults came, right? And then to figure out how much money was brought in by children or seniors, we would go their ticket price 8 times however many children or senior people came. And then the total would just be the sum of those two values. So there's our first linear system. The second linear system was attendance, or models attendance, and their total was 240. How was that created? Well, 240 is just simply all of the adults plus all of the children and seniors, and all of that should sum up to 240. So here's our linear system. Now we're being asked how many adults attended the early movie. The answer to that will be where these two lines intersect one another, where the qualities or the characteristics of both lines match. Okay? So, to put these lines into our calculators, we're going to need to turn them into slope-intercept form. So let's take the revenue equation and turn it into slope-intercept form. It's up to you which variable you want to call y and which one you want to call x. It doesn't really matter, just as long as you remember if you solve for, say, c in this equation, you also have to solve for c in the attendance equation. Okay, it doesn't matter if you solve for a or if you solve for c, just remember to solve for the same thing in both equations. Okay, so let's just solve for, let's solve for c. So it's a negative 11a plus 2370, and then divide everything by 8. So c is negative 11 over 8a plus 2370 over 8. And we'll just have to remember when we're going into our calculators that x represents the number of adults because we're replacing a with x, and y will represent the number of children or seniors. Okay, so just keep that in mind when we go to graph this. Let's take the attendance equation that's currently in general form. Again, we want to solve for c because that's what we solved for in the last equation. If you solve for a in the last equation, then you would solve for a in this one. So this guy would be negative a plus 240. So there's our two equations in slope-intercept form. Let's graph them and figure out how many adults came.
Alright, so let's graph this function here. Figure out how many adults came to our movie. So y is the number of children, x is the number of adults, and our first function for revenue is negative 11 over 8x plus 2370 over 8. All right, and y2 was negative x plus 240. That's for our population or our attendance model. And let's think about our x-min and x-max and all that stuff. X is the number of adults who came. So what would be an appropriate maximum? Well, the total maximum number of adults that could come would be 240, right? Couldn't be any bigger than that because our problem said that at most 240 people came. So we'll make the x max to 50. And same for the y max, right? That's the number of children that came. And it couldn't be any more than 240. So we graph it, and there's our point of intersection. And that point of intersection will be the point at which the conditions of both the total revenue, 2370, and the total attendance, 240, are the same. I made a boo-boo. The point at which the conditions for each function are met, right? So if 150 adults came and 90 kids came, or seniors, then the theater would make $2,370, and you can see if you added those together, that would be 240 people, right? So the conditions of both functions are satisfied at that point, thus our solution.